thank you for staying till almost the end of the day. And since that's a difficult time, I guess, for all, I thought of starting this presentation with a story. So basically, when I was 17, I faced a difficult choice, which was actually engineering on one hand and medical on the other. And 20 years later, I'm now a civil engineer with a PhD in conservation science. And you may think I make no sense, but actually I believe that buildings are like human beings. And imagine that you're in the center of a historic city and you look around you. What you see is basically buildings that look a bit old and tired, still gorgeous, but kind of wrinkled, isn't it? And that's because buildings do age like us, and they can suffer even more if they are exposed to bad conditions. So we may get a cold when it's freezing outside, and buildings do suffer when the water freezes inside their pores. So what do we do when we feel bad? We actually go to the doctor, right? And even though buildings cannot move, they still need their own doctor. And I'm a doctor for buildings. And having had already years of experience, I became quite good in following the conventional steps, which was actually to visit my patients, diagnose the disease, find out what caused the disease, stop it, choose the most appropriate treatment, and monitor the health progress. Yet I could feel that I could do a bit more for my patients, because actually being already ill may be exhausting, treatments may cost a lot of money, and sometimes they are incompatible and they can cause even further damage. So could we prevent this at all? And if so, how could we do it? And then I thought of us. If you think of us as human beings, what is the best mechanism that actually protects ourselves and is ready to start immediately the production of new cells and heal injuries just by itself? That's our beautiful immune system. And sometimes it may need to get boosted, but it is there naturally. So wouldn't it be amazing if our buildings had an efficient immune system that naturally heal themselves just when damage occurs? And actually what I can already tell you is that, for example, stone, one of the most widely used geological construction materials in the history of humanity, can be the perfect body for microorganisms that could fix cracks before they become critical. So using naturally occurring bacteria and the food they like, we can end up having materials with a self-healing system ready to work when damage occurs. So that's pretty much how I ended up becoming a doctor, but for buildings. And at my current position as a Newcastle University Academic Track Fellow at the Hub for Biotechnology in the Built Environment, biological self-healing for sustainable building and smart heritage conservation has been the center of my research, aiming to promote the adaptation and reuse of existing properties and heritage buildings, to develop disruptive smart technologies that can reduce the maintenance needs and offer radical solutions which align with the international targets for sustainable development. And that all fits under the umbrella, which is my vision to help construction materials and structures to remain active, to be able to maintain themselves independently, to serve to the society while being environmentally friendly. The good thing is that actually we can be optimistic already that we can achieve our future goals. And this has been inspired by my previous research project, which was funded by the European Commission. So bio-mineralization has been explored for consolidating porous materials and as a new class of self-healing cement-based building materials, but has yet to be explored for a range of environmentally friendly cementless materials. So how this self-healing cycle would work, you can see here a very nice scheme which shows porulated bacteria within porous media. These lead to mineral products containing tubes, to the spores. And when deterioration of the mineral exposes the spores, germination of new cells from spores causes further mineral formation and new spore encapsulation. So this project focuses on stone, lime-based composites, as well as earth-based building elements. And all of them constitute a significant part of masonry and heritage structures worldwide. We shouldn't forget that these materials are bioreceptive and suitable for biomineralization by nature due to their pore structure and composition. And they're also compatible with the healing products of biomineralization, such as calcium carbonate. So the flow of the experimental work that has been carried out so far is given in this slide. And to prove the potential of the mechanism to heal bulk materials, laboratory specimens were prepared and their absorptivity values were recorded. The specimens were then divided in 4 different groups. Group A was treated with bacteria and nutrients. Group B was treated only with nutrients just to check what happens with the naturally occurring mechanisms in the specimen, microorganisms in the specimen. Group C was only treated with water for comparison, and Group D was treated with dead bacterial cells and nutrients to control whether the dead bacterial cells can act as nucleation sites. So after the first healing stage, evaluation took place involving a series of analytical methods, which you can see in the box, and laboratory tests. So following these first treatments, water absorption was measured again to compare with the values before treatment. And in this graph, you can see a group of specimens where actually we have a decrease in capillary absorption for all specimens that were treated with bacterial nutrients, while we see no significant changes in the specimens where only nutrients or only water was applied. And another method that we used was, and that was also to evaluate the changes of the microstructure, was a portable drilling resistance measurement system. There is previous research that actually shows strong correlation coefficients when comparing these values with various standardized but destructive laboratory tests. And another benefit is that we can actually, instead of getting just bulk properties, this test records the in-depth profile of the materials, resistance to drilling. So we can detect denser microstructures, voids, or consolidated areas. And in this case, the DRMS profile showed a peak of high resistance for Group A specimens, which you can see here. And that was not the case for Group B and C. And then that happened in the area closer to the treated surface of the specimens. So scanning electromicroscopy was also used, and there is a clear evidence of newly formed calcium carbonate particles in Group A that was treated with bacteria and nutrients. That was not the case in Group B and C, while we had scarce presence of newly formed calcium carbonate minerals, but significantly less compared to Group A. In Group D that was treated with dead cells and nutrients. And the second row of photos shows actually the microscopic aspects attained using confocal microscopy in specimens stained with a dye. And that dye has the ability to stain all the newly formed calcium carbonate particles. And the results agree well with the SEM. Basically, what you can see above has been kind of repeated in a way in the second row of pictures. So following the first round of experiments, the second healing stage aimed at investigating the possibility of having bacteria spores which would survive harsh conditions and contribute to further mineral formation. So we took specimens from Group A that were treated with bacterial nutrients during the first healing stage, and we subjected those specimens to salt crystallization damage and sterilization. And the specimens were then divided in 2 sets. One set was further supplied with nutrients after damage, while the second set was only supplied with water for comparison. And then the whole set of analysis and tests was performed again after the second healing stage. And here you can see that DRMS confirmed the ability of this bacteria to cause mineral formation at the area closer to the treated surface compared to the control samples, which you can see in the right-hand graph. While we can see also that confocal microscopy proved the strong evidence of newly formed calcium carbonate in Group A. And what is very important for the second healing stage is actually that here in the SEM pictures, and here you can see Group A specimens after damage that were treated with nutrients, where we can see new mineral formation, while in the Group A specimens that were only treated with water after damage, we didn't see that with that microstructure. So the results proved the successful precipitation of the damage in previously treated specimens only with further nutrient supply. Just to sum up, there are considerable opportunities for biological self-healing masonry materials. They are bioreceptive and suitable for biomineralization. Both bacteria that we tried have induced significant differences in the microstructure of laboratory specimens, with S. urea spores having survived after chemical and physical damage. and germinated new cells. So it can be used for self-healing through bio-mineralization. Sufficient supply of nutrients is needed to promote healing. And overall, the sensitive healing and self-healing method seems ideal for reducing maintenance costs and offer compatible solutions where accessibility for maintenance or renewal is limited, such as in heritage structures. And current and future investigations involve the development of weathering-resistant biological self-healing systems for a wider range of masonry materials, exploring the use of different microorganisms, the possibility to produce other compatible minerals, the use of other storage mechanisms for nutrients, and so on. And the biological self-healing systems will be coupled with other advanced technologies targeting other properties, because we want to overall upgrade the performance of masonry materials. Side trials, as well as application in the experimental house of the HBBE biome, have been planned. And we also want to assess how heritage organizations and governing bodies respond to the use of these novel processes and materials in historic buildings, monuments, and artifacts, increase public awareness of such technologies, the importance of historic structures, and the potential to reduce environmental impact in construction through adaptation and reuse of such structures with smart technologies. And also the use of more environmentally friendly materials, even in contemporary architecture. And that's the end of my presentation. I only wanted to refer to the other two presentations that relate to this work. And one, hopefully you had the chance to see today during the poster session. And that was presented by Derek, the PhD student, and who focuses on rammed earth. And there is one more coming on Friday, and I encourage you not to miss it. It has to do with one of the prototypes that relates to this work. And yeah, it will be presented by Armand. And thank you very much.